So what is this talk about? I come from kind of an SRE background, software operations, for the last several years. And I've noticed in the last decade, we've kind of gone from running our systems ourselves by hand to building and running the systems that run our systems. Like, we've added an extra layer of abstraction here. And it's really good in many ways. It lets us do things we couldn't otherwise do. But there's a bunch of risks and considerations that come with it. And that's what this talk is about. If anyone has seen my previous year's talk at QCon in New York, it was kind of a Tales of Fail talk, and this too has a Tales of Fail element. So if you like, software operations, architecture, and failure, you are in the right place. Right, about me. I cannot work presentations. I am not a real astronaut, or a real presenter, apparently. I'm a senior staff software engineer at Slack Dublin, and before that, I was at Google for a number of years. I was a contributor to the Site Reliability Engineering, How Google Runs Its Production Systems book, also known as the SRE book. And I write for various places, including InfoQ, as of last week. And I do a quarterly column for Usenix's Login magazine. And, fun, interesting fact, I campaigned for a ban treaty against lethal autonomous weapons. And you should too, because we all know that software is terrible. We should not put it in charge of killing people. And on Twitter, I'm Laura Lifts. Okay, so reliability in the cloud. We all, we can cloud, lots of really smart people building really resilient systems, all this redundancy, all this failover, right? These things are designed from the bottom up to be resilient to any kind of hardware failure, from an entire data center on up. And yet, and I'm not going to pick just on Amazon, and yet, I'm also not going to pick just on Google. So that's, the top 3 kind of major cloud providers. They all have outages. We know this. We have to build our own systems if we're using the cloud. We have to build our own systems to be resilient to this as best we can. But consider a humble server. It's actually not unusual to see multi-year uptimes. It's pretty unusual to have your public cloud go for an entire year without some kind of major outage. This thing, it has no redundancy, just a single box running in one rack, no network redundancy to speak of, no power redundancy. So why are we failing to make our clouds more reliable than a single machine? Hopefully this talk will shed some light on this question. So in the old days, we had human beings. The human was in the loop. We were configuring our servers by hand, or we were sort of semi by hand. We were using scripts. We would have Puppet, or we would have Capistrano back in the day. But the decision to provision a new machine and set it up and verify it and put it in your load balancer pool, that was typically done by a human being. We weren't auto-scaling. We sized things for peak, plus 10% or whatever your magic number was, and we left things running. We weren't scaling up and scaling down. We weren't dynamic in that way. We didn't have job orchestration. Kubernetes and all these things were only a glimmer in somebody's eye. We lived in a mostly static world, mostly run by human beings. Times have changed. Now, this may not be the case everywhere. As our previous speaker said, the future is here, it's just not evenly distributed. But certainly, at the very, very large software houses, all of the public clouds, and any other sort of smaller software company that's running their own private cloud or running on Amazon Web Services or any of the other cloud providers' clouds tend to be using a lot of this sort of dynamic automated provision. The mantra in operations for the last decade or more has been to automate everything. Automate job orchestration. So no more provisioning by hand. No more scaling up and down to meet load by hand. All manner of routing, failover, load balancing, all this should be automated. And this is not wrong. It isn't wrong. A lot of this work is repetitive and there are downsides to it. But this is the change that we have wrought. In the parts of the future that are distributed, we have largely succeeded in automating away a lot of this work that we were doing in 2010. And that is the truth. Why? Money. In a lot of cases, money is the overriding pressure. I mean, we are business, right? We run our systems to support businesses. There are direct financial savings from some of these elements. So by using job orchestration systems, having multi-tenant computing, and by scaling our jobs up and down to meet demand if we're in a public cloud, either way we can save money. We also save money by not having to employ as many people to run our fleets. The mantra is automate yourself out of your job so that we don't need to have 10 people to replace you next year. And this makes a lot of sense. So it's just important to remember that money is the overriding reason that we do this. But there are a bunch of other pressures. One major other pressure is better performance and latency. So if you have a job that's being automatically scaled up and down to meet demand, it should have better latency because you have a lower chance of hitting a congested sort of, an overloaded instance. A lot of these systems that we're going to look at are related to how do you balance load, how do you distribute a load in a way that's kind of globally optimized. How do I route you, your traffic, to the nearest place where I can serve you without being overloaded. This is very good for your system's performance. This is very good for end user perceived latency, which, I mean, again, going back to the last slide, that's good for money, right? But we also want to reduce the repetitive toil of managing a large fleet. When you run a system with thousands or hundreds of thousands or millions of jobs and machines, you are dealing with failure constantly. If anyone was at Denise Yu's talk yesterday, she had a really adorable slide illustrating failures when Google turns up a data center, and had like a little computer with a pram. It was just gorgeous. Her art is so great. But it's real. We see failures constantly. And you cannot page a human being to deal with that every time you have any little failure. It's costly. It's repetitive work. Nobody wants to do this, right? We also want to react faster to routine hardware failures. We don't want a box to break and have a bad hard drive or whatever and sit there throwing errors until a human being comes along and takes that out of your load balancer pool. There is just no point in living that way. It's unnecessary pain for our customers. It's unnecessary stress and pain for us in operations. We want more consistency in production. And this is one of the big changes that we see in operations in the last few years, this concept of infrastructure as code. We don't want to be building machines by hand anymore. We want to be able to press a button, or better yet, have a dynamic control plane actuate an RPC and provision our instances of our services in a way that is completely consistent and completely repeatable. We do not want to be building pet systems anymore. And that makes a huge amount of sense. And we also want to reduce compliance risks related to engineers touching productions. Especially if you're in finance or dealing with any sort of payments or anything to do with kind of the federal government in the US or other governments, they get very picky about who is logging into your servers for debugging or for operational stuff, and you want to minimize that as much as you can. A lot of companies now are saying, well, can we automate all of our control and have humans never SSH in, just remove that access. And as an aside, I think that's very, very difficult to do, but you should be certainly removing that from routine operations. So there's a bunch of pressures towards this pattern where our systems are being controlled dynamically by some sort of a control plane system. Just as a little aside here, I'd like to call your attention to this wonderful diagram. Because this presentation has a space theme. Space themes are great for your presentations because all of the NASA imagery is Creative Commons by law. So this is an Apollo 14 spacesuit. It's got a sunglasses pocket on the right arm. I just want to call attention to that. Okay. So we've been talking about control planes and the sort of dynamic control plane pattern that we're seeing. It arises in order to control other systems and very often to solve global optimization problems. So let's look at a few of these. This is our simplest form. So we have some kind of a controller process. Our controller process is in charge. It's got some it's got some business rules. It's probably got some configuration. It might be accepting some sort of control input from human beings occasionally. And what it's doing is it's doing operations on our service instances. And these could be switches, or it could be jobs, like, sort of instances of some binary that you're running, or Kubernetes pods, that kind of thing. Probably these service instances are serving work PCs or web pages or something to someone else outside of this system. And probably they have some sort of load balancer pointed at them, but this is kind of outside the control plane diagram that we're showing here. And, I didn't put it in because, hey, this could be, pipelines that are processing data. A signal aggregator. This is the way that the controller senses what's happening in the service pool so it can react. Because typically these controllers are trying to keep some kind of the system in some sort of a status quo state, or a state that conforms to some kind of configuration that they have. So things change in the service instances. They get more load or less load, or they change state. They go healthy or unhealthy. And the signal aggregator will scrape that state from each of the service instances and make it available to the controller. So this signal aggregator, it could be Amazon CloudWatch, or it could be Prometheus, or any of these kinds of tools, Graphite. Or sometimes the signal aggregator and the controller are collapsed into one entity. Okay, here's a concrete example. So auto-scaling groups, as provided by all of the major cloud services. The idea here is I have a bunch of service instances, so running instances of my containers or my binaries or whatever it is. And I want to scale them up and down based on how busy they are. So you're going to collect metrics in some way, and this could be some sort of monitoring tool as provided by that cloud provider. Or you could be collecting things through some of your own monitoring tools and making them available to the auto-scaling logic. This could be something you've built yourself. I've seen hand-rolled versions of this kind of thing. So you're going to collect metrics, which could be CPU load, could be some sort of count of the number of requests served per unit time. And based on that, your autoscaler is going to scale that pool of instances up and down. So busy, put more in. Not busy, take some out. Saving you money on your cloud bill. Great. Simple enough, right? So, but this is the same architecture as we saw on the previous slide. This is a control plane. One of the really interesting things that people forget about autoscaling is the system is bigger than just this. You're making an assumption here that your system is not going to be scaled for the peak of your traffic. And therefore, in order to serve the peak of your traffic, you are dependent on this auto-scaling system working correctly. And you're also dependent on whatever process you have to provision a new instance and to get it registered with whatever load balancing pools or DNS or whatever it needs to be registered with. And that varies by system. From experience, very often a lot of that stuff is made from janky Python or whatever. You don't want this. If you have this pattern, whatever is needed to provision your instances are part of your core production system now, because it's required in order to serve your peak load. And it's surprising how often things like this become fragile. Here's a Kubernetes cluster. Kubernetes is the hotness, so I'm not going to explain what it is, but basically it's a system for orchestrating and managing your jobs. So you say, hey, Kubernetes, here's a bunch of nodes. You manage these, you run VMs on them, and you distribute jobs, instances of the tasks I want to run through this cluster. So the kubelet is a process that runs on each of the instances in your Kubernetes cluster, and it monitors the load and the health of the pods, which are your jobs, your working production systems that are running. You got a control plane, which is the Kubernetes master, and it's the same system. So this is an instance of our control plane system that doesn't have a specific signal aggregator because the control plane just talks to the kubelet directly. It should be noted Kubernetes, it doesn't let you scale that large. It lets you scale up to about 5,000 nodes, and partly that will be because of the control plane limits in terms of how many signals it can get from how many nodes. I have seen job orchestration systems that scale much larger, but they had that level of indirection with the separate signal aggregator. So, getting a bit more complicated. Those first three instances we saw are kind of like a regional or local or zonal controller. You might run like multiples of these. Like you might run multiples of these in one data center. You might run one per region, but they're separate. And that will solve some of your problems. Like it will solve your problem of, I want to scale this job in this location to meet this demand, or I want to run this Kubernetes cluster in this location. But sometimes you have bigger problems. Sometimes you have problems where you need to think about global demand. Very often this arises in the realms of networking and load balancing and routing, because if you've got a global backbone or you're trying to steer user demand to your systems in a global way, you need to think about the problem in a global way. The thing about global problems is you cannot optimize for them locally. You can make them work by doing things locally, but you're going to have waste and potentially reduced performance in parts of your system where the local parts of your system are not able to optimize the kind of the global view, right? And remember, this is one of the pressures that we see towards these global control systems. Let's look at an example. So DNS load balancing. If you want to route user traffic to the nearest instance of your service, if you're running multiple places around the world, you need some sort of DNS load balancing to do it, or an anycast network, of which possibly more later. So this will be something like the NS1 has a geo load balancing product. You say, hey, NS1, my service is here, 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 and here, and please route my users to the nearest instance that has capacity to serve that load. So you don't know where your demand is going to spike up at any particular time or any particular geography. And let's say, I have a data center in Singapore, data center in Hong Kong, data center in Japan. And a bunch of load pops up in Asia because I do a launch or whatever. If your load balancing system knows what the capacity of each of those sites is and how much load each of those sites currently have, it can steer the demand to the sites that are optimized for nearness and for not being too busy. And this is good. So what you need here is you have your service pool A and B, and they're pushing up into their signal aggregator how busy they are. And you push that up to your global controller, which is going to program out all of the DNS servers for basically what percentage of load they should send to each of these, each of the sites, based on how much capacity they have. And this is good. This works really well. This works a lot better than just random, where you could be sending users to a place with an arbitrarily high latency. I mean, you don't want to send users in Japan to the east coast of the US if there's capacity nearer. But you also don't want to send them to an overloaded site or a site that might be down for maintenance. So this is why we use systems like this. And it's worth noting here, our DNS servers, they're not actually acting on the service instances, so it's missing one element of the control plane pattern, but we're still seeing the signal aggregation and the global controller elements of it. This is a sort of a simplified version of an SDN WAN controller. So specifically, it's a simplified version of Google's B4 SDN WAN controller. So B4 is Google's software-defined networking backbone. It's global, so it's a network that spans the world. And what you want to do with that network is you want to look at where load is coming from and going to, and you want to figure out how do I use the paths I have optimally to serve that load at the lowest latency. So it's a global optimization problem, and load pops up in different places and sort of comes and goes. One of the reasons for that is that B4 is it's used for sort of batch type work. So if you need to copy, some terabytes of data from here to there, you would use the network priority that gets it onto the B4 WAN, as opposed to the other one that they have. Anyway, so you need to be constantly looking at what the demand in this network is and optimizing for it. And so you've got a bunch of switches all around the world in the different data centers where this network is. And they're sending metrics up to the collection system, which is sending those up to this sort of global optimizer service, which looks at configured bandwidth limits for different users, and it looks at the flows, and it figures out how to optimize that, and it pushes that configuration out constantly to these things called TE, for traffic engineering servers, which program paths into these switches to create this global network of switched paths, which are efficient in network terms. So this is your complex global dynamic control plane. But the dynamic control plane is not just any automation. This is automation that tends to control very important parts of your production systems, like, are my jobs running? Like, is my network working? Is my DNS working? These are mission critical things. This is not something that's doing, ancillary things like checking do my backups work, which is also very important, but your systems won't fall over today if they're not, right? It's sort of an architectural smell. This automation means something. This automation matters. So with these systems, we're mission control now. And that's what the title of this talk comes from. We don't run our systems. The robots that we build, the systems we build, run our systems. And it's harder. This is a more challenging engineering task, and it can go wrong in a bunch of ways. This is the Apollo 13 lunar module, because we have a space theme. Now, I'm guessing probably most people have seen the movie and know some elements of this story, so I'm not going to tell the whole thing. But what happened with Apollo 13 is they had an accident, as we all know, and it's all heroics and things. When the accident happened, everyone back in mission control was super confused. They were getting these really, really, really confusing signals from the telemetry that they were seeing. Here they are with their bemused faces. So they were just getting a bunch of signals about the electrical voltage fluctuating up and down, and pressure fluctuating up and down in cylinders, because their electrical system required the oxygen cylinders to provide oxygen to the hydrogen oxygen fuel cells. This part is not my technical part. But anyway, the big point here is these guys were confused. They were super confused, because they were looking at these very abstracted signals that were being sent from space. And how did they figure the problem out? The astronauts figured the problem out, because they were there on site. They heard a bang, and that they could see on their gauges, they could see how the pressure was fluctuating up and down, and they could see gas venting out into space, right? They could see what was going on because they were there. They had the mechanical sympathy and the direct observation of their systems. And that is kind of one of the big things that we lose, right? This is the service module, and you can see here, it's all exploded and stuff. Yeah, so that's why Apollo 13 was sad. Yeah, so, and then there's a whole great story. There's a really good part in Charles Perrow's book, Normal Accidents, that deals with this story and emphasizes this particular part about understanding what happened and the sort of the mechanical sympathy of being on the spot, which is really worth reading. So anyway, they got home. They managed to go around the moon, and the whole thing where they cobbled together oxygen things from the wrong thing. It was, well, very exciting. But they got back, and then NASA had an IPO. No, they didn't. They're just happy because their astronaut's back. Okay. So because we're mission control now, it's harder for us to understand our systems in production. Okay, now on to the tales of fail. That was just the introductory tale of fail. That was sort of justifies the title of the talk. So we're going to talk about dynamic control plane incidents. I'm going to talk about some cloud providers. No judgment. We all have issues, and these providers are brave enough to, and helpful enough to give us accurate tales of what went wrong. So not judging, not throwing shade, just trying to look for lessons. So this one's pretty old. It was the night before Christmas, and API calls relating to managing new or existing elastic load balancers started to throw mysterious errors. Their running instances of their services seemed to be unaffected. Their team was puzzled because many API calls were succeeding. They were able to create and manage new load balancers, but not to manage existing load balancers. And some things were just failing. What was happening? They were confused. They spent some time being confused, like 4 hours, which is a long time when your systems are down. But they started to put together the fact that running load balancers were okay, unless there was a configuration update, or someone tried to scale them up or down. Once they figured that out, they mitigated sensibly by disabling those scaling workflows. And then they dug in. They noticed that there was missing state data, and that was the root cause of the service disruption. They did a data recovery process, and they merged in whatever changes since their last snapshot. And it took about 24 hours to get back from this. So that's a pretty serious thing when you can't create new load balancers or change your existing ones, because that's a pretty important workflow. And it turned out that a dev had run something in prod that should have been run in dev, and it was an accidental deletion, and it was sort of a data management issue. But what I really want to take from this incident is how difficult and how long it can take to debug when things go wrong with these kinds of control planes. And this is why making the actions and the operations of these control planes really as understandable and clear as possible to the human operators is really key. A big part of the danger and the risk that these things add is the fact that operators now need two mental models. So in the old days, you just needed to know how your load balancer worked, and you went in and you made the changes by hand. Now, at Amazon ELB, the operators need a mental model of how the ELBs themselves work, but also a mental model of how the ELB control plane works. And unfortunately, when you have two different things that are now interacting, that's more than twice as complicated as your first thing, or as two of the original things, right? The interactions add to the complexity. So this is about 4 times as hard to do. Nancy Levison talks about this a lot. She's an MIT professor who talks a lot about engineering safety, very often in military and industrial contexts. And she has good diagrams where you kind of have the system that controls the system, humans, what we do, as we saw in the previous example, is part of the sort of the unpredictability and the difficulty of controlling these systems. Very often you have control actions taken by humans, sort of interacting and competing with the control actions that are taken by the control plane system. So life just, especially when things are going wrong, life just gets a lot more complicated. There's also the very old saw, which is the ironies of automation. And this has been studied a lot in the context of aviation. You automate something, and that's great. You make it more consistent, you make it more reliable. You mean that it takes away some human work. But it also means that humans become less familiar with the day-to-day hands-on operation of that system. So therefore, when your automation breaks or goes wrong in some way, the humans are now further away from that system and have less chance of being able to manually intervene quickly to resolve it. So, ironies of automation. Here is our second tale of fail. So, moving on to 2016. Google Compute Engine lost all the external network connectivity for 18 minutes globally. So that's your entire cloud network down. How did this happen? Somebody submitted a config change to remove an old unused IP block. This should be very safe. Unfortunately, there was a bug. Some sort of race condition happened, and the system decided to remove every single one of the GCE IP blocks. So very sensibly, they have a canary system. A canary system is a small part of your system where you can send upcoming changes to see what effect do they have and make sure that they're within expected parameters. And they did this, which is great. But unfortunately, it seems their system just threw the answer away, which is not so great. So this is the second bug that we see here. So we have an initial race condition bug that produced a completely incorrect configuration. We have a canary system that was there, but not working correctly. So they rolled this out. They're advertised over BGP, Border Gateway Protocol. And they advertise the same blocks everywhere, all around the world. And this is known as IP Anycast. What that means is you have this sort of magical virtual IP address, servable from a bunch of places. And what the internet just does is it routes you to the nearest network point where this is advertised. And nearest in network terms doesn't mean geographically nearest, it really means cheapest. But usually it's also the nearest, so this is fine. So the thing about IP Anycast is if it's available anywhere in the world and you're probing it, that will still work fine. Yay, until the last one goes away, and then it's completely down. So they were probing this system, and it was fine, as it was gone in 99% of everywhere. And then it goes from, it gets turned off from the last place, and everything is bad. So their rollout process didn't have the signal that it needed. Their control plane lacked that signal. There are better ways there are other ways of monitoring your Anycast systems. You can, for example, you can put in a special query that that will tell you exactly where the request is being served from, and that can give you more signal about what's happening. If you suddenly notice that all your probes are coming back from a smaller and smaller and smaller pool of results, that will give you a signal. So that's something that you can do, but they were not doing this at the time. But that's a counterfactual, and we don't like those. But just to say that it's a complex systems failure, multiple bugs and latent problems. And you've got multiple dynamic control planes going on here. So there's the network configuration, but then there's also the control plane that's doing the canarying and checking the network configuration. And both of those went bad in interacting ways. So what do we learn from this? We learned that testing is a real challenge. These systems have bugs, as all systems do. And the trick is you get your nasty failures when you have multiple bugs. So it's not just testing in terms of unit testing that you need, although you need that. You need to be doing testing in an integration, an integration systems testing. So spinning up a little sandbox with all the instances of the related systems and putting them through scenarios. So in an ideal world, you would have an integration test for your control plane system that would spin the whole thing up and have it try and put through a bad configuration and make sure that the canary system catches it. But these are very expensive and quite difficult to do. They're worth the investment, I think, to make sure that your failure scenarios are all still running. And it's worth doing these in your staging systems and production systems as well as a real disaster test. Because if you don't, one of the days it may bite you. Last year, Google had a big network outage for cloud, but also for their other Google services. Elevated packet loss and network congestion for 4 hours and 25 minutes, which is quite a long time. So Google's machines are segregated into multiple logical clusters, and each of them have their own cluster management software. So like the Kubernetes clusters that we saw earlier. They had a maintenance event happening in just one physical location, and this was the trigger for the outage. So it should just have brought down some infrastructure in one site for maintenance. So it could have been power or network or any sort of maintenance that requires downtime. Maintenances on that scale become common events, not just daily events, but multiple times daily events. So you automate them, right? The automation software becomes a control plane because it's taking in these configurations and it's bringing down pieces of infrastructure and draining traffic away. And it's monitoring to make sure those drains are happening correctly. The automation control plane was also interacting with their software control plane for the network. They had a bad configuration, which basically said, hey, turn off all the network control plane everywhere. So that was a misconfiguration. Now, this shouldn't have been allowed to happen, but due to another software bug somewhere else, it was allowed to happen. The control jobs, it's like what we saw with the B4 SDN WAN earlier. What they're doing is they're doing this global optimization and trying to program the network to efficiently route the packets without dropping anyone's packets, without introducing any extra latency where possible. So without the control jobs, the network will still stay doing what it was doing before, but it won't be able to adapt to things changing. So after a little while, it'll turn itself off. It'll withdraw the network because it's going to go, okay, right, well, the network control jobs, they're not there. I can't adapt, turn off. So they actually managed to root cause the incident fairly fast. But the problem was their network was in a very bad shape, and that impeded their ability to get everything back up and running. And also, their network control plane, it runs as a consensus-based replicated system. But this had incorrectly brought down all instances in a bunch of locations. So it had lost its state. That state wasn't being backed up anywhere useful, so they had to rebuild that from scratch, which lengthened this outage. So again, we're seeing multiple misconfigurations, bugs, permissions problems. We have multiple dynamic control planes, and it was very hard to predict that particular sequence of events. Data loss. These systems are critical stewards of the state of our systems. And data in these systems has to be treated like production data. You need to have all sorts of plans for dealing with failure or data loss or data corruption in your control planes. It's a key consideration when you're building these things. And again, may I stress, we don't just roll these out of janky Python and assume that they're going to stay running forever. They need real engineering going into them. As we see, the blast radius for these incidents can be really large. It can be your entire network. That's really serious stuff. Testing your fail-safe behavior. It's scary, particularly if you do, scary in dev even. It's easy not to do this. It's easy to assume that the behavior you've designed in for your system to carry on, to fail static when your control plane is down. It's easy to assume that that works the way you intended. It's scary to test it because you're putting risk into your system, and we hate this. You don't want to be the person to push that button on that disaster test and take everything down. But it's necessary. It is necessary to have ways to test this. This, by the way, it's from the report on the Challenger disaster, and it shows the O-rings that had no fail-safes. It's an early classic of resiliency engineering. That report is well worth reading. So what can we do? Is it hopeless? Are we lost? Are we forced into? We are basically forced into having these dynamic control plane systems. If we're large enough, we need to have at least some of these in order to mitigate, the sort of the human toil and all of the downsides and uncertainties that come with having humans manage our systems. So get to a reasonable scale, and that scale is probably only in the hundreds to low thousands of instances, and these systems become inevitable. So we have to do something. So one thing that's pretty important is to use regional or zonal control systems where feasible. So instead of having one system that tries to knit the entire world together, unless there's a really, really, really good reason why you need that, try and have them split up. It means that the maximum blast radius of any of these is much less. They need to be tested at least as carefully as your main production systems, and probably more. They need unit tests. They need not to be made out of janky shell scripts, although shell scripts can also be unit tested. They need integration testing. They need to be tested in production. They need occasional testing that their failure modes and data recovery processes and all of these things are really working the way you intend. This is a big one. You need to plan for the time, and this is significant time. Whoever is running these systems needs to have time budgeted to stay familiar with what's actually going on under the hood. So time to run all of your backup, your backup tools, your manual processes for recovery, for staying familiar with what's actually happening under the hood. It's so important, because if you don't do this, this is something that you kind of don't take into account the first year or two where you build one of these systems, because everyone has been working with the underlying system for ages. They know exactly what's going on with it. They know how all these operations work, but fast forward 3 or 4 years, people have forgotten what they knew, and you'll have a whole bunch of new people on the team. So you need to plan constantly for exercises, drills, and time to stay familiar with underlying operations. And this is one of the hardest engineering tasks, I think, around these systems. You should put guardrails around them. Your automated system, your control system, should not be able to withdraw every IP block that your cloud is managing. It should not be able to shut down every job that your system is running. You need to put limits on these systems, because they can and they will have bugs. They can and they will have negative interactions with other systems. You should put guardrails in, and you should test these guardrails constantly in your integration tests, because these guardrails are a really important part of the business logic of your dynamic control plane system. And sometimes humans are better. Large installations will need some dynamic control planes, but you probably don't need to have 10. You don't need to build a dynamic control plane system for every little thing. Maybe sometimes what you need is a little script that a human will actuate and check the output of and hit OK, and the operation rolls out. That's a semi-automated state, but it's not this fully automated autonomous control plane system, right? So consider whether you need them. This is another big one. When you're designing these systems, they had to be designed to be able to be understood by a human operator. There are all sorts of things you can do. One really nice pattern is to add a status page to these kinds of systems. And that's literally a web page that your system will serve that will tell you exactly what the system has done recently and why, and what it is going to do next, if known, and why. Logs, as usual. Traces tend to be maybe less applicable to these systems, but could still be useful. Another really, really, really useful thing where you have multiple control systems interacting, make them all log all of their significant operations to one place. So it could be your Slack channel, it could be any other sort of log ingestion mechanism. Just one place where people can go and look at the sequence of events. When you're trying to debug weird interactions between multiple control systems, that's what you need. You need to be able to say the sequence of what happened and figure out why. Overridable. Systems are systems. They are fragile. They are brittle. They will have bugs. Humans are adaptable. Humans are able to deal with the unexpected and make sensible decisions. So humans always need to be in charge. A really good pattern when you're building these automation systems is to build a big red button. And a big red button is just some sort of state bit that you can flip somewhere that says, hey, system, don't run anymore. Just stop what you're doing until this bit gets flipped back. And ideally, any on-call engineer in your organization should be able to flip that, because anybody might notice that these systems are running amok. And sometimes, if you have a system that's literally taking down your entire network or all your serving jobs in multiple locations, you just want to be able to say stop. So that's a feature that should be built in to these kinds of automation, a way to stop them really fast. And if we do all these things, maybe one day we'll be able to build a cloud or a large computing system that has better uptime than a single machine does. So that's the talk. I should always say that we're hiring in Dublin. I don't know if we're hiring here in London. We're hiring in the US. I don't actually have time to hang around afterwards for questions. I think there's like 2 minutes left of this session, because I do have to go to the airport. But if anybody has any questions, my Twitter is Laura Lifts, and I will reply to any tweets. Thank you.